Okay. Thank you all for coming. Today, I'm glad receiving Dr. Kam-Biu Liu in our institution at C14 Lab at CENA. Okay, it's a pleasure for us receiving you here. And I also would like thank you all to give you some professional information. I'm glad receiving about Dr. Kam-Biu Liu and in our scientific institution activities of Dr. Liu at C14 Lab at CENA. Okay. Dr. Liu is a pleasure for us, professor and chair here at Department of Oceanography and Coastal Science to give you some State University. Professional researcher of FAPET project receiving dynamics of American mangrove and austral and boreal limits on secular and decadal scales. Okay. Dr. Liu is expert professor in bioenvironmental reconstitution studies regarding climate change and coastal dynamics and some extreme events using rudimentary stratigraphy of pollen, carbon dynamics, isothermal mangrove, C14 dating, austral and boreal limits on secular and decadal scales. Nature. Dr. Liu is science expert professor communication environmental proceedings of the National Academy regarding climate change, remote sensing, coastal dynamics, and some extreme higher than 12 elementary stratigraphy of pollen, carbon dynamics, now viewers decide for data, X and limits, and Leo. It's a great pleasure for us receiving you nature. Dr. Liu is an expert nature communication. Now it's proceedings of the National Academy regarding climate change, remote sensing, coastal dynamics, and very much higher than usual elementary geography, pollen, carbon dynamics, now viewers decide for data, X and limits, and Leo. It's a great pleasure for us receiving you nature. Dr. Liu is an expert nature communication. Now it's proceedings of the National Academy regarding climate change, remote sensing, coastal dynamics, and very much higher than usual elementary geography, pollen, carbon dynamics, now viewers decide for data, X and limits, and Leo. It's a great pleasure for us receiving you nature. Dr. Liu is an expert nature communication. Now it's proceedings of the National Academy regarding climate change, remote sensing.
Something like 30 years ago, after I came to Louisiana and LSU, before that I am originally from Hong Kong, and I went to Canada, the University of Toronto, to do my PhD. And so most of what I did before I went to Louisiana was working on boreal forest pollen at the other end of the world. But after I came to Louisiana, I realized that every year the Gulf of Mexico coast in the US was struck by hurricanes. Now, so I came from Hong Kong, and I am quite familiar with typhoons. But in Louisiana, we have hurricanes. And so that started to get me thinking that as a paleo-environmental scientist, and I was thinking, can we find a geological record of hurricanes going back to thousands of years? This is what I did in Canada, in the boreal forest. We go back to 10,000 years ago, at the boundary between the Holocene and the Pleistocene. And so that's what got me started thinking of finding a research method to reconstruct the history of hurricanes going back to thousands of years. And that's my motivation for starting this new field of science. Now, so that was a definition that I gave in a book that I co-edited. It's called Hurricanes and Typhoons, and I wrote the first chapter of that book, and I outlined the method of the principles and methods of paleotempestology, and that's the definition that I gave. It's a young field of science. At first, it was a new field of science, but now it is young. I would not call it new anymore. But it studies past hurricane activities by means of geological and also historical or archival techniques. Now, so I will talk about the geological proxy techniques today. And when I first conceptualized the principle and the methods, I was thinking of finding a coastal lakes, and particularly a back barrier lakes or marshes or wetlands. That is, a lake or a wetland that is situated right behind a barrier beach. Maybe there's sand dunes on the beach. And I was thinking, well, when a hurricane was making landfall, it creates a storm surge. And if the hurricane is very strong, then the storm surge would be very high, and it can overtop the sandy barrier, the beach and the sand dunes. And as a result, a layer of sand would be washed into the bottom of this back barrier lake. And of course, if you look down from the top, it will be in the form of an overwash fan. But when we take a core, then it will be a sand layer. So my thinking at that time was that, if we take a series of cores from or along a transect, from the bottom of the this back barrier lake, we should be able to find sand layers like this or this, by means of, what we call the rubber boat science, coring. And we should be able to find multiple sand layers, and if we can use radiocarbon or other kinds of techniques to date those sand layers, then we can reconstruct a chronology, a history of prehistoric hurricanes going back to hundreds or even thousands of years. So that was my early concept, and that is, based on the principle that we will try to detect this overwash deposits in back barrier lakes and also marsh or wetland sediments. And since then, we published our first paper in 1993, but since then, other researchers, they have thought of other kinds of methodology or techniques, and now we have more tools in our toolbox. And for example, I started doing overwash sand layers in back barrier lake sediments, but from about 1997 onward, and isotope geochemists, they found out that the hurricane rings are characterized by highly negative or depleted delta 018 signals. And so they were using this principle and applied that to tree rings, to apply that to speleotherms, and to try to detect that signal. And also some people were using blue lagoon sediments, deep holes in marine sediments, or what sedimentologists call tempest ice in shallow water marine sediments. So now we have more tools in our toolbox, including tree rings and speleotherms and blue hole marine sediments, and some historical climatologists were using historical documentary evidence. Now, so the just to reinforce what I said, the principal idea and the methodology in this field is to detect the evidence of salt water or seawater intrusion into otherwise, ideally, if that is a freshwater lake, then we can detect the saltwater or seawater intrusion signal. And this could be done by geochemistry and isotopes as well. But so in addition to doing the sedimentology, and of course my training as a palynologist, I also looked at pollen, dinoflagellates, and diatoms, and even phytoliths. And in the last 10 years or so, we started using XRF techniques to look at the elemental chemistry of the sediments, but all to try to detect that signal of saltwater intrusion into otherwise low salinity coastal lakes and wetlands. And here I want to give you an example of what I mean by detecting the saltwater intrusion signal. And this is a sediment core, just a short core, 60 centimeters. It was taken from coastal Alabama, 2 states, to the east of Louisiana. And this site that is called the Gulf State Park is a state park that I started, working on since the very early 1990s. So we've been working at this location for more than 30 years. There are 3 lakes, and we've done a lot of work on Lake Shelby, but I want to bring you to this lake here, Little Lake, which is just a small lake. It's the smallest of the 3 lakes in the coast. And you see the coast was characterized or isolated from the Gulf of Mexico by a series of beach ridges, very well-formed beach ridges. But you see that there is kind of the beach ridges are truncated here. Now the lake is completely isolated from the Gulf. No saltwater influence. It's a freshwater lake basically. But you know that in the past, you know, there was erosion of the lake. So that means that there was some exchange of seawater with the lake water here. And so here in this core, we got a basal radiocarbon date, CENA at the bottom, of about 1,250 years. But within the last 1,200 years, we have 7 sand layers. And 2 of them, the yellow bands here, are very thick, prominent sand layers, but they're also thinner sand layers. Now, so in order to show that those sand layers are brought in by overwash and marine processes coming in, we did a dinoflagellate analysis. Dinoflagellates are more common in estuarine and marine waters and is very rare in freshwater or low salinity environments. And so we found that at the top we don't have any dinoflagellates, but where we have a sand layer, we have dinoflagellates. And at the bottom, it's very thick sand layer, a lot of dinoflagellates. So that is an indication that these sand layers, some people ask me, could that be brought in by rivers? And so, by the way, the lake there's no rivers coming in, so that's part of the answer to the question. But to show that these are indeed marine processes that brought in the seawater, we can see that dinoflagellates, which are more common in seawater, associated with the sand layers. So this is an illustration of this principle that we can use the occurrence of marine indicators to reconstruct the overwash processes brought on by hurricanes. Now, but my thinking kind of started to change, or not to change, but broaden a little bit. In 2005, and again 2 years later in 2007, I got a grant from the National Science Foundation, NSF. I was collaborating with some human geographers. These are people who are working on cultural conditions, and we try to, and when we have a project that was conducted in a place called the Mosquito Coast in Honduras. The Mosquito Coast is in the easternmost part of Honduras. This is a very isolated area. There is a movie that is called the Mosquito Coast that was done, like many years ago. By the way, that movie was shot in Belize, not really in the true Mosquito Coast. But the Mosquito Coast was probably the most isolated and remote part of Honduras because there are no roads going there. And in order to go there to do field work, we had to charter a small piloted kind of airplane, and we flew to that area, and the plane landed in a soccer field in the middle of the village, and that's how we got there. And my human geography colleague was trying to look at how the ethnic groups, different ethnic groups on the coast were affected by hurricanes. Because this part of Honduras and also adjacent Nicaragua was badly hit by a hurricane called Hurricane Mitch, which is a very destructive hurricane and killed up to 18,000 people because of precipitation and landslide and flooding. And so that was a collaboration with my cultural geography colleagues. And when we went there, there were 3 villages that I and my cultural geography colleagues were doing some field work, and my colleague was interviewing a lot of people, holding town hall meetings with the local villagers. And because there are three different ethnic groups, this village called Pattaya was inhabited mostly by Garifuna, mostly of African, and Caribbean origins. And then this village here, Palacio, was inhabited by the Latinos and the Mosquito Indians, native population. And Cocobilla, there was a village right on this sandbar, was inhabited by only Mosquito populations. And so we were calling this Lake Ibans and also calling this Laguna Bacala there. But after we got there, we found out that the villages were badly affected by, not by the strongest hurricanes. In 2005, you can think of some famous or notorious hurricanes. Hurricane Katrina was 2005. It flooded the whole city of New Orleans, and killing more than 1,300 people in New Orleans, and that's Katrina, followed by Hurricane Rita. And then if you live in Florida, you may remember Hurricane Wilma that year. But in the late season, there was there are three hurricanes in the late season, October and November. But the last hurricane, very late in the season, was Tropical Storm Gamma. Now, these are not very strong hurricanes when it affected this region, but these three storms collectively brought more than 21 inches of rain, which is like a quarter of the annual precipitation in that region. So what it did, or what they did, was that it caused tremendous flooding of the area because the grounds were already saturated, and so it was tremendous flooding of the area. The rivers, this is Rio Negro, brought a lot of river water into this area and the surrounding areas as well. And so all the water were brought to here, and it caused tremendous pressure to erode the beach ridge. And there is this village of Pattaya that is situated right at this location. And so this flooding, the elevated discharge of the river did, was that it broke or it breached this coastal barrier from the inside out. Now, so this is the effect of fresh water. This is not coming in from the storm surge or the overwash. This is the opposite process, fresh water going out. Now, so, and it created a breach here. And, the village next to it, Pattaya, was severely damaged, and that was a disaster, to the local population. And another example of, the effects of the fluvial flooding was that before these three hurricanes, you see that this was a river with a mouth here, but and also this same map, you see that it was a river that was separated from the sea, but afterwards it created an opening. Again, it's by fresh water pushing out. Now, so that's got me thinking that when we are looking at the geological impacts of hurricanes, we cannot just look at a unidirectional process. It's not just salt water or seawater coming in, but rather fresh water from the rivers can play a very important role in not only the erosion that I just show you, but also in sedimentation as well. So my thinking started to change. And then I started doing research. It was also funded by the National Science Foundation. And so let's bring you back to the Gulf of Mexico. This is Mississippi, Alabama, and Florida. And here is a bay. It's called the Mobile Bay. The city of Mobile is right to its north. And on, this is Mobile Bay, sorry. And here is a small bay that is on the side of Mobile Bay. This is called Weeks Bay. And Weeks Bay, if we do a transect along the edges, the vegetation changes from coastal marshes, salt marsh, brackish marsh, and then fresh marsh, and then some swamp forest. And if you go further up, a little bit higher elevation, you have hardwood forest. And then when you go further up along this river called the Fish River, and you have even pine forest, and also next to the pine forest, we have pitcher plant box. This is Sarracenia, an insectivorous plant. It's beautiful landscape. And we took sediment cores from this red dot here, which is larger map. I know this is not a very clear map, but anyway, so we took sediment core, and the Fish River is flowing in here. But anyway, so we took a series of cores, but I just want to show you this one today, and that is a short core, only 45 centimeters long. But in the middle of the core is a prominent sand layer, about 8 centimeters thick. And so the loss and ignition is the sand layer, low organic and low water, with a radiocarbon date. And with more research, I compare with the historical record. I figure that this is corresponding to a hurricane in 1772 that is recorded in the historical record. And so no doubt that I think this sand layer is a storm deposit that is created by a hurricane. The question is, what processes formed this sand layer? Was it from the storm surge, marine processes, or is it from the fluvial processes? So how do we show that? And I had a colleague visiting me from China at that time, and he's a diatom researcher. And so I took him to the field. We took some surface samples, and surface samples along a transect from the mud from the middle of the bay. Certainly is brackish, highly brackish to marine water, and then all the way to the marsh, and then all the way to the pitcher plant box and through the forest. And it turned out that we found that in the freshwater environments is dominated by this assemblage of diatoms. So this assemblage here represent freshwater environment, and those samples, surface samples, they were collected from the bay closer to, or from the salt marsh, they are dominated by this saltwater assemblage. And so when we did the diatom analysis in the core, in this sand layer, we found a distinctive assemblage of diatoms. And when we compare with the surface samples, this assemblage certainly are mostly derived from freshwater environments. Now, at that time when we did this, I did not have the capability to do XRF, so I did not do XRF, in this core or other geochemistry. But from the diatom evidence, I think it is pretty convincing that this is not only seawater coming from the Gulf, but rather this is the river flooding and bringing fresh water from the pine forest, from the box, the pitcher plant box, and deposit this sand layer here. Now, so my thinking started to change, or at least to be broadened. I'm not saying that hurricanes do not bring seawater into the site, but we cannot ignore fresh water or the fluvial processes, and that is the principal lesson that we learn from these studies. All right, another more recent and even more famous example. I think a lot of people had heard of Hurricane Harvey. In 2017, there were three very strong hurricanes that make landfall in the United States. And the first one is Harvey. It hit the Galveston, Houston area. And then the next one is Hurricane Irma that hit Florida. And then another one is Hurricane Maria that almost destroyed the infrastructure of Puerto Rico. All the power structures, were destroyed in Puerto Rico, and it caused more than 3,000 deaths in Puerto Rico. Now, so Hurricane Harvey is a unusual hurricane. When it made landfall, it was a Category 3 with 130 miles per hour wind, very strong hurricanes. But what made this hurricane especially destructive was that it moved very, very slowly. After it made landfall, it hung around, this is the Houston area, eastern Texas. It hung around in eastern Texas for 2 days. And it brought tremendous amount of rain. And in fact, it brought up to 1.5 meters of rain, more than 60 inches of rain in this small area. Now, so it caused tremendous flooding, and Houston was badly flooded. And not only Houston, but a lot of the rivers had record-breaking discharge because of the precipitation. The one thing I want you to pay attention to is that look at these dots here, which indicates the extent of flooding. The dots are not on the coast. The dots are a little bit behind the coast. So this flooding was not because of the storm surge from the sea, but rather this is fluvial flooding from the rivers, freshwater flooding. And of course, along the coast, you have what people call compound flooding. It's a mixture of seawater and fresh water. And so I have been working with a colleague, Professor Harry Williams from the University of North Texas on this, and we got a grant from the NSF to do this. And we tried to look at the sedimentary signatures of Hurricane Harvey. And from this satellite image, you see that, well, this image comes from this area here. You see that here we have an intercoastal canal here. This is a man-made canal that was dug, but the canal mainly received fresh water coming from behind this coastal marsh area. But the satellite image captured the fact that there were plumes of sediment-laden fresh water coming from the marsh at the back towards the coast. Now, so this is very clear evidence that freshwater flooding, hurricane, heavy precipitation, can carry a lot of sediments to the coast. Now, so that is a wake-up call that other than just looking at saltwater intrusion, we cannot ignore freshwater input and fluvial flooding from behind. Now, so with that much sediments being brought in by fresh water, and so our question was that how do we find it in the sedimentary record? My colleague, Dr. Williams, has been working in this area for more than a decade. And in fact, he had taken multiple cores from this area. And in this marsh, he took monoliths and also sediment cores. And he already documented very well that we found multiple clastic layers. These are mostly made up of clay and silt, fine-grained sediments. Some layers have more sand. But anyway, so he has already found that there are multiple layers sand or silt or clay layers that can be attributed to previous hurricanes, like Hurricane Ike. Hurricane Ike was that it directly hit the Galveston, Houston area in 2008, and that was a very strong hurricane, brought overwash and storm surge that completely destroyed the structures, the houses on the Bolivar Peninsula. And so this layer was attributed to Hurricane Ike. Now, but after Hurricane Harvey, when we did field work there, we found a new and fresh clastic layer on top of it. This is very fine-grained deposit, and this is undoubtedly the Harvey layer, because that layer was not there before this hurricane. And this layer was up to 7 centimeters thick from this core, CL1, and 7 centimeters. And Harry, my collaborator, he did a lot of work and already established that in that coastal marsh, the average accretion rate was about 0.38 millimeters or centimeters per year. So from this study, we can infer that one single deposit, that was the fluvial deposit from Hurricane Harvey, can bring up to the equivalent of maybe 10 to 20 years of average marsh sedimentation. And this illustrates the importance of freshwater flooding and the sediment input that it can bring to the coastal marshes. Now, this has important implications, because a lot of people are concerned about the effect of sea level rise on the coastal wetlands, because if the wetland, the accretion rate, cannot catch up with the rate of sea level rise, then we have land loss. We have the coastal lowlands would be flooded in another few decades. Now, so but one single hurricane can bring up to 10 to 20 years of average sedimentation to the coastal marshes, and that means that this is a very important contribution. And this Harvey layer is characterized by it's very fine grained, so only 5 to 10% of sand. And compared with the lower layer, this is Hurricane Ike, 2008. Ike, because we know that this is storm surge and overwash, Ike contains a lot more sand. This solid black line is the sand percent here. Now, so the fluvial deposit is finer grain, although it is also very low organic matter like the Ike layer, but the texture is much finer. And there is this very thin marsh deposit that represents about 9 years of deposition between 2008 Ike and 2017. And so we have this. The marsh was growing back, on the surface of the Ike deposit. And we also did some XRF analysis, and in fact, this paper was published just in 2019, so less than 3 years ago. And we found that this is one of his earlier cores, and we found Hurricane Audrey, Ritter, and Ike, and this distinct sand layers, and the Ike layer and the others as well, characterized by very high ratio between chlorine and bromine. This CL-Br ratio, we use that as a marine indicator, which is basically a salinity indicator. But the new core that we took, this is the Hurricane Harvey deposit, and this is the Ike deposit. Hurricane Harvey deposit was characterized by very high titanium, which is terrestrial in origin, and so again confirming that the material and the water is coming from the back, from the fresh water draining the marsh and the slope, around the basin. And okay, here is another study that I did, again with an NSF grant, to work in Baja California. This is a different region. You know, this is not affected by the Atlantic hurricanes, but by the Eastern North Pacific hurricanes. And we went to La Paz, which is the capital of the state of Baja California Sur, and we caught some coastal lakes there. And here is a lake that, you know, this is the city of La Paz, and this location is facing the Gulf side, the Gulf of California, or, you know, in Spanish is the Sea of Cortez, and this is the Pacific side. So this lake, we call it Crescent Lake because of the shape, like a half moon shape. It is situated in a very sheltered location because, you know, a lot of the hurricanes were coming up from the south or some from the west, and it is very protected from, you know, hurricane effects, storm surge or whatnot. And this lake is this is mangrove. This is especially Rhizophora. There is some Avicennia as well, but Rhizophora was the dominant here. At the back, there are some Avicennia. At the back, you know, this is kind of a salt fret at the back. We took multiple cores from this lake. So this is a panorama of the lake. It's kind of a half crescent shape, and it is surrounded by steep slopes on three sides. On this side, and there's a highway on the side, but it's very steep slope going down. And so on three sides, it was surrounded by steep slopes. You see along the highway, you have slope wash or you know, soil slope erosion. But on this barrier, you have some succulent plants, mostly the Chenopodiaceae, and then here these are mostly mangroves. So that is an interesting physical setting because you know, it got me to start thinking that where would the sediment come from in this lake? And we can think of primarily two main sources of extraneous sediments. One source is that if we have, by the way, the lake is normally not affected by the tidal currents. It's isolated, although there is a very tiny channel here, but you know, it's high enough that normal tides do not get into the lake. But if we have storms, hurricanes, or in that location we could have tsunamis. And so if we have very high storm surge or tsunami, then we can imagine that overwash can happen and bringing marine waters and sediments into the lake. But another very important source that I don't need to think about in the Gulf Coast, because you know, in Louisiana, as you know, Erica and Dr. Cohen know very well, we don't have slopes in Louisiana. Landscape is completely flat. So, but this is a different kind of environmental setting, because I can imagine that this is a desert area. If we have hurricanes bringing a lot of rainfall, and sometimes one storm can bring up to a year of precipitation in that area, you can imagine the soil erosion of the rain, and there is very little vegetation to hold the slope, the soil. And so from this all three sides, you can imagine that when we have a hurricane, a lot of sediments can be washed from the slope into the lake. But that would be terrestrial, that's not marine. So here is a picture of a core. And even visually, by looking at it in the field or in the lab, I found that there are three types of clastic layers. One type is the very thin layer, but you can still see it. You know, this is all peat here. But between the peat, you have this very thin layer that is, you know, different color, different texture. And in the core, we found many of this. Well, you know, when it's pointing down, this is a clastic layer. So these are clastic layers. But very thin layers. Another layer here is this one. This is a much thicker layer, but if you look at the sedimentology, these two kinds of layers, they are very low in organics. The green is organic, so very low organics, meaning that it's mostly silicates. You know, that is the composition of the sediments. But also, it is low in carbonates. The brown curve is carbonates. Now, so there is very little carbonate content, and we know that sediments from the sea, from the ocean, is more rich in calcium and in carbonates and so on. But the third kind of layer, this one has even shells in it. So it's unmistakable. This is coming from the marine area, like this one here. You see that the organics were very low, the green curve dropped, but the brown curve, this is very rich in carbonates. It's partly because of the shells, and also but the sedimentary content. Even, you know, we don't burn the shells, burn the sediment matrix. It's rich in carbonates. Now, so these three kinds of sediments mean that they are formed by different processes. And here is the core, and we got a series of radiocarbon days. The bottom goes back to 6,000 years. And so we see this, the red arrows indicate the thinner, the first type of sediments. And, you know, they are marked by a dip in the water content and in the organic matter content. And even these thicker ones that were dated to about 4,000 years ago, this one is also is low organic, low water, but also low in carbonates. But look at this one here. This one is dated to about 5,600 years ago. It's low in organics, but it is high in carbonates. And at the bottom, we have this sediment here, and actually it's mixed with some shells as well. And this is high in carbonates, so that was part of the environment that was connected to the sea. Now, so if we consider these thin layers were coming from the slope, representing slope wash, this is the contribution of fresh water. But it's not just the water, but it was the slope wash. The rain causes the soil erosion and slope erosion that, you know, we had not thought about it in Louisiana. But, you know, in a landscape like this, in fact, you can see that, you know, throughout much of the last 5,000 or 6,000 years, it was the slope wash that was predominant. But if we go back to, you know, like 5,600 years ago, we interpret this, you know, this might be a tsunami event, because, you know, it brought a lot of marine sediments into here, and in the early phase of the lake, the lake was connected to the Gulf, and so it has more marine influence. So, you know, I'm trying to tell you that, you know, how my thinking has been broadened over the years, you know, from different studies. And let me bring you to Louisiana now. This is coastal Louisiana, a place that both Erica and Dr. Cohen are very familiar. This is Port Fourchon in coastal Louisiana. And in Port Fourchon, we have a lake a back barrier lake. This is a continuous barrier beach, and it's called Bay Champagne. It's a very shallow lagoon, and with the barrier is only about a meter more or less, but this area is experiencing very rapid coastal retreat. The lake is mostly brackish to saline. The salinity is somewhere between 27 and 30 parts per thousand. The lake is not deep, it's only about 2 meters, but at the back, especially on 3 sides, there are mangroves. There's only one species of mangrove, and that is Avicennia, is black mangrove growing there. And just to show you this is a very dynamic landscape, because even in the last, if we look at this series of pictures, 1953 and 2009, so this is only about 50-some years, a little bit more than 5 decades. And we have a reference site here, that this yellow dot, in 1963, the lake was almost a full circle, and this site was in the middle of this lake here. In 1978, that's only 25 years later, the coast has already retreated by this much. The yellow dot is fairly close to the coast now, and then 2009, that yellow dot is right behind the beach. So very fast coastal erosion and shoreline retreat here. And in 2008, this coast was hit by 2 hurricanes, and both very strong hurricanes. Hurricane Ike, that I just mentioned, that hit Galveston and Texas. A few weeks later, it was followed by another hurricane that's, the first one is Hurricane Gustav. And then a few weeks later, it was Hurricane Ike. So Hurricane Gustav made landfall directly in coastal Louisiana. If I can go back to here, this is the first storm, Hurricane Gustav, and then the second Gustav. It made landfall in Texas, but it was a huge hurricane, so it brought very strong storm surge to Louisiana as well. But Gustav is the direct hit at this site. Anyway, before the first hurricane, before Gustav, I worked with some physical oceanographer, and we deployed 2 bottom-mounted CTD instruments on the lake bottom, and the instrument can help us detect storm surge, the water depth, and storm surge, and also temperature, and also conductivity. And we deployed it at these 2 locations here. And these are the 2 curves. One is showing the storm surge. This is the depth of water. And of course, if you have the storm surge, then the water is deeper. And so you see that the Gustav storm surge was 2.7 meters because it's a direct hit. And Hurricane Ike is only 1.5 meter. But what is surprising, that was the total surprise to us, that we expect that the salinity will increase because the seawater was coming in, right? But then when we look at the salinity measurements, the salinity did not increase, but rather it decreased during and right after the hurricane strike. Now this is, and we double-checked the equipment. We thought that, well, maybe this is a measurement error, but turned out that the equipments were working perfectly. And same thing for Hurricane Ike. During the storm surge, there was some increase in the salinity, but then after the days to a week after, see the salinity actually dropped. Now, so the only explanation is that this is fresh water coming from the back, and because then when I first worked on paleotempestology, I thought that we only have to look at the sea, to have the seawater coming into the coastal lakes and marshes. Now, so fortunately, in this site we took multiple cores before these 2 storms, and also we took cores after the storm. And so we took cores. This is before the 2 storms. We took this in 2007, and we found at least 5 sand layers near the top of the core. And then after the 2 storms, we went back, and this is the top of the core. We found, in this core, we found 17 centimeters of fresh sediments. And so it was all 17 centimeters, but how can we tell which one is Gustav and which one is Ike? At that time, our suspicion was that you see that there is kind of a sloppy, semi-consolidated section in the middle. So my interpretation was that this whole thing was Gustav. And then a few weeks later, when Ike came, it disturbed the top of the Gustav sediment and forming this sloppy section, and then the top of it is Ike. Now that was my hypothesis, but how can we prove that? And so at that time, I already had the capability of doing XRF, and so I did the XRF analysis and to list different kind of chemical elements. And this is a short core, less than 45 centimeters long. And we found, this is the top. In this particular core, we have about maybe 14 centimeters. In another core, we have 17, but it's the same. We suspect to have, 2 layers here. And then below that, we have, other sand layers that are separated by kind of organic clay sediments. But, I want to just bring you to these 2 elemental ratios here. One is the chlorine to bromine ratio that I talked about before, and the other is the calcium to the iron ratio. And both we can use as marine indicators. You can see that the sand layers generally have higher CLBR ratio, or in some cases the CAFFE ratio. The sand layers have higher ratios than the organic sediments between them. So just another way to show that we can use these 2 ratios as an indication of marine water intrusion. But still, why is one storm, and if you look at these 2 layers here, the Ike layer at the top has somewhat lower ratio than the Gustav layer, if you look at the CLBR ratio here. And so what makes the difference? And so we want to show that these 2 ratios are indeed representing seawater influx. So we took surface samples from the beach and also from the marshes behind it. And here are the surface samples. At the bottom is from the barrier beach. This is the beach sand. And at the top, this was taken from the marsh, lower salinity environments. And we can see that the beach samples with higher salinity, closer to the sea, has higher ratios. And the samples from the marsh, they have lower samples. And so we lower ratios. And so just to show that these 2 ratios are useful. And another ratio is the strontium. See, the beach samples has higher strontium than samples from the marshes. Just a few years ago, I have a PhD student, Marianne Dietz, who did a PhD dissertation on this site. And she looked at the characteristics of these 2 hurricanes. And so again, there's 2 hurricanes here, and she used some of my cores, core 48 and 52. But first of all, she compared the 2 hurricanes. Now, so Hurricane Gustav is a direct hit. And so the wind was stronger, the pressure was lower. This shows the barometric pressure. See, Gustav, landfall, the eye was almost at the site. So very low pressure. And the wind speed here, Gustav is higher. Ike, the second hurricane, the pressure was not as low because it was farther away. And the wind speed also is lower than that of Gustav. But the precipitation and also the storm surge, this is from my curve, that Gustav created a higher storm surge than Ike. Now, but she found that from a salinity reading in Deschamps, there was some record here that, and this was also from my study, that the salinity in both locations dropped. But she found from a stream gauge that Gustav, even though the wind is stronger, it brought less precipitation to the site. We cannot find a weather station right at the site, and so we can only use this discharge from the river as a proxy for precipitation. And so Gustav, the discharge was lower, and Ike, even though it made landfall farther away, but it was a big hurricane, and it brought more rain to this site, and so the river discharge was higher. Now, so the two hurricanes, and that's the paper that we published last year, and the topic was the title was differentiating hurricane deposits in coastal and sedimentary records. Two storms, one layer, but different processes, and that's the lesson that we learned. Now, and she did more XRF analysis on this two cores, 52 and 48, and the Ike layer at the top. It is Ike layer. You can see that it is predominantly it's a terrestrial. In fact, if you look at this core, it's even better because the blue means it's a positive anomaly, and so it's dominated by titanium and the iron. These are terrestrial elements indicating water and sediments were coming from the back. But if you look at the Gustav, the terrestrial elements are below average, but the marine elements, the calcium and the strontium, they were above average, positive anomaly. Now, so from the meteorological data and the hydrological data to show that the two storms are different, and that explains why the two storms, one storm, the Gustav, that is marine processes dominant because it's a hurricane that makes direct landfall at the site causing a higher storm surge. But Ike was hit further away, but it brought a lot of rain, and so that results in more freshwater influx into the site. And in fact, we did pollen analysis on one of the cores too, and at the near the top, corresponding to the hurricane Ike layer, we found Sagittaria pollen. Sagittaria is a very common marsh plant, but primarily in freshwater marshes, in low salinity environments. And we found salinity, Sagittaria here, but and you can see that in other storms, these are older sand layers. The dinofractulates may be predominant. So not every storm is bringing in a lot of fresh water. There's some storms in the past that can bring in more seawater. So the dinofractulate could be higher in other storms. All right, so this is the lesson that we learned from Bay Champagne or Port Fourchon. To summarize in a nutshell, now we realize that storm deposition is a hydrologically complex process. This is, when a hurricane comes, the sedimentary and hydrological impact is not a one-way street. We cannot just look at the sea and try to detect the salt water or seawater signal, but rather we cannot ignore the fresh water or the fluvial input from the back. So this is my kind of a few concluding thoughts. So since the early days when I started working on paleotempestology, the premise or the hypothesis was that the storm deposition is driven by storm surge or overwash processes. So we try to look for saltwater intrusion. But now there is a lot of literature to show that as a result of global warming, hurricanes are becoming wetter because it carries more moisture. Warmer air carries more moisture, simple principle. But also the speed, the translation speed, the forward speed of the hurricanes are getting slower. That means hurricanes can stay at the same place for a longer period of time. It gives them more time to bring more precipitation. So now we have Hurricane Harvey, that can dump 60 inches or 1.5 meters of rainfall. And Harveys are getting more common nowadays. Now, so the society now is interested in the freshwater flooding process. There are more people, not more, but a lot of people who are drowned inland, by river flooding, rather than on the coast. Now, so that goes back to the title of my talk, a new research frontier in paleotempestology that I've been working on in the last few years is to assess the relative contribution between fluvial and marine processes in coastal storm deposition. And we need to use multiple proxies. I think this morning I was talking with Professor Pasenda and also Professor Cohen in the lab. And we need to use multiple proxies in order to solve this research problem. And because storm deposition is a hydrologically complex process. And finally, just to do some advertisement of this field, paleotempestology is not only of purely scientific merits, but rather it is a policy relevant science because nowadays compound flooding, both seawater and fresh water, are becoming more and more of a societal problem. So I think I am a little bit over time, and I'm sorry for taking up more of your time. Thank you very much.
Okay, thank you very much, Professor Kam-Biu Liu, for this excellent lecture talk. I learned a lot with this. I guess we will discuss a lot too. And I would like to know if you have some questions, doubts, and so on. Marcelo.
The microphone. I think that. Could you hear everything? Yes. Okay. I think. Okay. Because you're transmitting. Yeah, your transmission. Thank you very much for your presentation. Your talk very good, didactically perfect. My question. Actually, I have two questions. At the beginning of the first, we could associate it, the thickness, grand size of these sand layers in the middle of mud layer to intensity of hurricanes in that point of the coast?
In general, that relationship is still true, that stronger hurricanes will bring in thicker layers and coarser sediments. Now, so but